Okay, thank you. First, I'd like to thank the organizers for putting together such an exciting conference and for inviting me to speak here. I'm a believer in the unity of physics. I don't like it when people are put in boxes. One person is a particle physicist, then there's a field theorist, and a string theorist, and a condensed matter physicist, and so forth. We're all physicists, and we shouldn't be described like that or put in such categories. And I'll demonstrate it today using the topic of duality in 3 dimensions. I'll demonstrate the unity of physics, and you will see that some of the people I will refer to are clearly people who cannot be put in such narrow area, that people who had contributions to different branches. And finally, I would like to say that it's ironic that I'm going to use duality to demonstrate the unity of physics. So I'll be talking about 3 recent papers I wrote with Witten, Senthil, Wang, and my student Sin, papers that came recently, and there were 2 related papers, that came out the same day as that. And I'm going to start the talk, with a historical perspective, but I'll give the historical perspective from more modern point of view, and I will show how 3 different lines of investigation, which were almost independent, put the almost in parentheses, converged on the same set of ideas. The first came from mostly the condensed matter people, although prominent particle physicists made some important contributions. So this would be one route. Another route is the supersymmetric route. And the third one is the large N, or ADS-CFT route. And this would be a nice example how ideas from different places come together, and the fact that they come together give us more confidence that the picture is right, and they give together a complete and coherent picture. Oops, keep going backwards. So let me start with the condensed matter thing. And some of the people here are recognized as particle physicists, or field theorists, or string theorists. And this is the idea of statistical transmutation. It was realized that if we take a massive particle which has spin 0, and we couple it to a dynamical gauge field with the Chern-Simons term, the particle can change its spin and its statistics. So it is as if this particle is a fermion. Or the other way around, we can start with a fermion and convert it into a boson. And this has been extremely powerful and successful in the theory of the fractional quantum Hall effect, in ideas of composite fermions. There's a trick known as flux attachment, and so forth. However, I should really emphasize that this idea that a massive first quantized particle, a single massive particle, non-relativistic, can change its statistics is a much weaker statement than a full-fledged quantum field theory of massless scalars or massless fermions could be related, and so that massless scalars can change their statistics by being coupled to a gauge field. Continuing with the condensed matter route, this is work that was done in the early 80s. Originally, the first paper was by Peskin, who is a particle physicist, and this is the idea of particle-vortex duality. So we have a duality here between 2 theories. The theory on the left is a complex scalar field phi with a phi-4th interaction. We are in 2 + 1 dimensions. We tune the mass term to 0, and we flow to the infrared. And shorthand notation for that is this Lagrangian. When I put the coefficient 1 here to highlight or to underscore the fact that I'm only interested here in the infrared physics. I don't care about the short distance behavior, only the infrared physics. And this is a conformal field theory. We have a lot of data about it, both theoretical and numerical. And this theory is known as the XY model, or the O2 Wilson-Fisher fixed point. And it has a global U1 symmetry that rotates phi by a phase, and we couple it to a background field, big B, that couples to keep track of the symmetry. On the other side of the duality, we have a different theory, which is very similar to this one. It's the same XY model, but it's not coupled to a classical background field, but to a dynamical field, denoted by little b. And throughout this talk, gauge fields, which are background fields, will be denoted with uppercase, and dynamical gauge fields will be denoted by lowercase. So the theory on the right is a gauge version of the theory on the left. The symmetry that rotates phi hat is no longer there, this global symmetry, because it was gauged. But instead, we got another symmetry, which is known as the topological symmetry or the magnetic symmetry that the B can couple to. So this duality is well known. It was tested numerically, and there's no doubt that it's right, but there's no actual proof, analytical proof, that it's true, and this is common in dualities. Oops, keep going backwards. And there is a map of the operators between the two sides, which showing that the duality is non-trivial. On the left side, the natural operator to study is phi itself. It's a charge, scalar field, and that's the order parameter. The natural operator on the right is a monopole operator of little b. And it turns out that the correlation functions of phi are the same as the correlation functions of this monopole operator. We can also compare the mass term. We can turn on a mass term for phi on the left and a mass term for phi hat on the right, and there's a relative minus sign between them, showing that when phi gets an expectation value and the U1 symmetry, the global U1 symmetry is spontaneously broken, on the other side, phi hat gets a mass and the gauge symmetry is not Higgs, and vice versa. Here is another duality that was also proposed by condensed matter people. The theory on the left, so before we had a boson-boson duality, this is a boson-fermion duality. The theory on the left is the same XY model, and it was argued to be dual to a theory of fermions interacting with gauge fields. And the gauge field here is denoted by this little a here, the gauge field in the Dirac operator on the right. So this is another duality, which is in a way more dramatic than the previous one, because we have bosons on one side and fermions on the other. And the theory on the right is what is known as QED, U1 with one electron in 3 dimensions, and it's also known as U1 level a half because of the parity anomaly. But there are many puzzles. Oops, I keep going backwards. There are many puzzles. First of all, the arguments in the paper suggesting that this is right involve particles of fields with fractional charges. So there's an issue of charge quantization. They also have Chern-Simons terms in the derivation that are fractional. So it's not clear what to make of that. Another objection that was also raised by other people is that the theory on the left is manifestly time reversal invariant. The theory on the right is the characteristic example of a parity anomaly, so it doesn't look like it has time reversal symmetry. How can we have a duality between a time invariance, time reflections, time reversal invariance theory and a theory which does not have that symmetry? Also, the theory on the left is a bosonic theory. We can formulate it on any manifold. We don't need a spin structure. No need to truth, it doesn't even have to be a spin manifold. The theory on the right has fermions. So how can we have a theory that depends on spin structure be dual to a theory that does not depend on spin structure? And finally, among the people who study various field theories in 3 dimensions, the actual behavior of this theory on the right, what this theory on the right does in the infrared, is still being debated. And there are confusing numerical results about this theory, and this is something that is being debated. So this is the status of this duality. We had boson-boson and boson-fermion. And the next one is a fermion-fermion duality. We have a free fermion on the left, coupled to a classical background field big A. So this is a free theory. And on the right, we have an interacting theory of fermions, again, the same U1 level a half. And this duality was proposed by these people in various forms, and it was motivated by studying the physics of the lowest Landau level at half filling, and was also used in topological insulators, specifically in something called the T-Pfaffian state. Now, here, the puzzles, well, whenever we have some of these, we also have these puzzles. The puzzles here are even more serious, because before we argue whether the duality is right or wrong, we should make sure that the 2 sides of the duality actually make sense. And here, we see a coefficient which is improperly quantized. We have 1 over 4 pi. So the theory on the left makes sense. The theory on the right, as it stands, does not make sense. We can say that what we call A is not A, and maybe we need to put some factors of 2. This will only move the problem around. It does not resolve the puzzle. Also, the theory on the left is a free field theory. It suffers from the parity anomaly, but up to the parity anomaly, it's time reversal invariant. And the theory on the right seems like it's not. It's the same QED with 1 electron, the theory which has a parity anomaly. And finally, the infrared behavior of this theory is debated. So that's what I wanted to say about this condensed matter route. I'm now switching to this supersymmetric route, and the considerations here are totally different. The flavor of the ideas, the nature of the ideas are totally different. So here we start with some dualities in 4 dimensions with n equals 1 supersymmetry. Again, these are only infrared dualities, very much like the previous dualities. And in the 90s, they motivated a whole set of dualities with n equals 2 or with n equals 4 supersymmetry, coming under various names. And these dualities in 3 dimensions also use particle-vortex duality as an ingredient. More recently, most of these dualities were derived upon compactifications from 4 dimensions. This is very common in dualities. We have a duality that we do not know how to prove, but if we assume that it's right, we can derive other dualities. And then when we perform consistency checks of the other duality, it gives us more confidence in the original duality, and that's why we call it a duality web. So that led to many more checks and led to many more dualities. And here, because the theory is supersymmetric, we can perform many more calculations, and people have done many calculations computing partition functions and so forth, give us, again, more evidence that the duality is right. It was also related to string duality, because some of these dualities were motivated by string constructions, so it's, again, connection to another root. And if we give masses to the particles, and we decouple them, these dualities end up being the level rank duality, which can actually be rigorously proven. So this is another test. We flow to something that is familiar, and not just familiar and can be rigorously proven. It does not prove that the dualities are right, but again, it gives us more confidence that we are doing something right. Now, these people suggested that if we have a supersymmetric duality, we can turn on supersymmetry breaking operators on the 2 sides of the duality and flow to a non-supersymmetric duality. This is much less rigorous because the flow, once we break supersymmetry, might not be smooth. There might be a phase transition. But it gives us something that we could guess, some nice motivation to guess these dualities. So this is what I wanted to say about the second route, the supersymmetric route, and I'm moving now to the third one, which will again have totally different flavor and totally different style of reasoning. And this is the ADS-CFT route. And here is a long list of references, and that's incomplete, even though it covers almost the entire slide. Here it was noticed that the same 4-dimensional bulk theory, this Vasiliev theory, has 2 different boundary duals. One of them is a theory of bosons coupled to Chern-Simons terms, and the other is a theory of fermions coupled to Chern-Simons terms. And if we have the same bulk theory dual to 2 different field theories, we can forget about the bulk and just say, here are 2 field theories that must be dual to each other. So this is a purely field theoretic statement, and it can be checked using large N technology. And there's a long list of people who contributed here, and the list is incomplete. And the tests are of, again, totally different nature than the previous ones. Free energy was computed, etc., etc. So that's yet another picture. Now, Ofer Aharoni put all these pieces together of the supersymmetric route and the large N route, and he spelled out 3 concrete dualities, and we added a 4th one, this one. And the common thing about them is that we have scalars with some 5/4 interaction on the left, and we have fermions on the right, and they're coupled to gauge theories with some level rank, something that looks a lot like level rank duality, for example, SUN level K and UN. UN has 2 different levels. The details are not of this particular map are not important for us for the purpose of the talk, but they are absolutely essential in order to get the story right. If you change one sign here or one factor of 2, the whole thing falls apart. So this is what Aharoni suggested, and this was motivated by the following arguments. First, it fits the large N picture. This is when we take N and K to infinity with fixed ratio. So this was one motivation. The second motivation is that it fits the supersymmetric picture that we had before. If we give masses to all of these, we flow to level rank duality, and baryon monopole operators match between the 2 sides of the duality. But as before, this leaves puzzles. And I'll now enumerate puzzles, and then I will try to, depending on how much time Chiara gives me, I'll try to answer most or all of them. So first question, this was stated as a fact, is it true for any value of n, k, and nf? Now we have three different integers that appear here. It was motivated by large n, but now we have more integers. Is it true for finite n? Second, question we've asked before, how can a theory of bosons be dual to a theory of fermions? One of them needs a spin structure and the other does not. More generally, what's the relation between these proposals and the dualities of the condensed matter people? And recall that there we had problems that some coefficients were not properly quantized, and there were puzzles associated with time reversal symmetry. Next, whenever we have a duality, we have to be very careful how we map the operators between the two sides of the duality. And an efficient way of doing that is to couple the duality, to couple the Lagrangian to background fields, background gauge fields for the global symmetries. And once we do that, we often need to add various counterterms that depend only on the background fields. Having the correct counterterms is essential in order to match the observables between the two sides. They also allow us to promote the background fields to dynamical fields. Next questions, are these assumptions independent? There were three parameters and four different dualities. Are they independent, or is it, as it's common in dualities, assume one of them and derive others? And finally, which is perhaps most interesting, are there other dualities in the same list? Should we add more objects to the list, the dualities of different kind? So in order to do that, we are going to be very bold and take this statement and substitute n equals k equals nf equals 1. Just blindly substitute it in. And notice that this was motivated by large n, and we are going to substitute n equals 1 and see whether we land on our feet or not. And here, the first thing that we see is this proposed duality, which I'm going to assume for the rest of the talk. We have three fermions on the left, and this is the Wilson-Fisher fixed point coupled to a dynamical gauge field B with a Chern-Simons coupling, level 1, and coupling to a background field A, which we identify with the background field here. Now, we have many dualities here. Most of them are between interacting theories. And it's often the case that we have many, many different interacting descriptions of the same fixed point. One of them is preferred if it's free. So in this case, we're talking about a theory of all the descriptions we can give it. This one is best because it's free. And as a free field theory, we know what we're talking about. The theory on the right looks interacting, but we have to we're going to check that the theory on the right reproduces the results of the theory on the left. So the theory on the right, despite appearance, is actually a theory of a single free Dirac fermion. So let's check it. The first thing to check is the global symmetries. Both sides of the duality have global U1 symmetry, and we wrote very explicitly how the background U1 couples to them. Second, time reversal. Time reversal on the left is manifest, except the anomaly. On the right, it looks like it's not time reversal invariant because we have U1 level 1 here. However, if we use the particle-vortex duality of phi, we can show that the right-hand side is actually time reversal invariant. So the time reversal image of phi is what we called phi hat before. So it's the vortex field is the time reversal image of phi, and I'll say more of that later. Conversely, if we assume that this duality is right, let's just assume this duality is right, then we can derive the ordinary particle-vortex duality as following from this one. So that's again something that is common in dualities. We can also map the operators between the two sides. The basic operator on the left is just a free fermion. The basic operator on the right is a monopole operator. And because of this term in the Lagrangian, the monopole operator carries charge under the gauge symmetry of B. This is what Chern-Simons terms do. And therefore, to make it gauge invariant, we have to multiply it by phi. So this is the map. The fermion is phi times the monopole operator. And you can check that this object has spin a half, and it carries charge 1 under U1A, which agrees with what we would expect from that duality. We also map the mass term. The mass term for the fermion on the left is the mass term for the boson on the right. Now, on the left, we know that this mass term does different things depending on what psi is, and we give it a mass and so forth. And we'll see that on the right, it also does different things. It either Higgses the symmetry or not. So let's do that. So as we deform by this side, by this thing, so the theory on the left is gapped, and we have a massive fermion with spin 1/2. The theory on the right, whoops, I can't do this thing. The theory on the right, we have, so phi is massive, we just give it a mass, so phi is massive, and it is charged under U1b, and therefore it's charged also under U1a, and it's mapped to the massive fermion. So on the right, in the massive phase, the duality between these two theories is the standard statistical transmutation. But the statement we are making is a lot stronger. We are making a statement about the massless case, when these theories are, this theory on the right is an interacting massless theory. And in the other phase, U1b symmetry is Higgsed, and then the system has vortices. The vortices have spin, and they are charged under U1a, and again, the vortex is mapped to the fermion. So we see here again this business that under time reversal, psi goes to itself, but phi goes to a vortex field. That's why time reversal symmetry is so hidden on the right-hand side, because it acts non-locally on the fields. We asked something about the spin structure. The theory on the left needs a spin structure because it has fermions. The theory on the right also needs spin structure because this Chern-Simons term here is a spin Chern-Simons term. But this is a little bit more technical, so I'll go quickly on that. If A is not an ordinary gauge field but a spin C connection, then we actually don't need the choice of spin structure on either side. And that's of course good, because using that we're going to resolve all these puzzles with spin structure in the other theories. Once we have a duality in hand, so we assume this is right, there is a machine that produces many other dualities. So what can we do? We can take this duality and on both sides of the duality add an ADA term, a Chern-Simons counter term for A, add the same term on both sides. We can also promote A to be a dynamical field, and then we create another background field. We can add another background field to it. We can also use other dualities, put parentheses around some of the fields and recognize, that's a duality we already had, let's replace it with something else that we had before, and then this way we'll generate more dualities. And I said repeat because it's like we can go back to the beginning and turn the crank again and find many more dualities. So what do we find? So now it's a straightforward exercise. The first thing that we find is this duality. It's very similar to the duality I had before. It was a boson-fermion duality. On the left, we see the same Wilson-Fisher fixed point, and on the right, we see this QED with level 1/2, but with an important counter term that has to be added in order to make the duality right. So first of all, this duality is now derived from our assumption. That's number one. Neither side, as it stands, the theory on the left does not need a spin structure, but it looks like the theory on the right does need it. But if A is a spin C connection, again, we don't need that. And we can map the operators, and we can check the flows and make sure that everything works correctly. And as in the previous example, time reversal symmetry, which was one of the objections to this duality before, works, and it works in a non-trivial way because it maps, on the left it maps phi to itself, but on the right it maps psi to another fermion which is non-locally related to it. So this way we resolve these puzzles. We can also find the fermion-fermion duality. So here we have a free fermion on the left, and on the right it looks like a very complicated theory, but in fact it's not that bad. This is a fermion coupled to a dynamical gauge field little a. This is again our U1 level 1/2. And we have another gauge field little b, and the two coupled to each other. Now I want to emphasize that all the coefficients here are properly normalized, and they're very important. You change one of these coefficients, the whole story falls apart. So first of all, the coefficients are properly normalized. Second, one might be tempted to integrate out b because the Lagrangian is quadratic in b, so this is just a Gaussian integral. But this is analogous to integrating out a massless particle. One is not allowed to integrate out a massless particle because it introduces non-locality. Similarly here, if we just focus on this term, this is U1 level 2. It's a non-trivial topological field theory. One should not integrate out this b. If one does integrate out B, ignoring this thing, there will be a penalty to be paid, and the penalty is that we end up with Chern-Simons terms with fractional level, and not only that, we find precisely the theory with fractional levels that we had before. So this theory, this duality, can be interpreted as the proper statement that replaces the previous fermion-fermion duality with the fractional levels. And all the other objections are satisfied. So there's a long list of things, additional things that we did, and I checked them here. First of all, there are many more dualities. I just gave examples to connect to things in the literature, but there are many more dualities, including many new dualities. We can add the Chern-Simons, gravitational Chern-Simons counterterms. That's another consistency check of the whole story, making sure that the framing anomaly works correctly under this duality. So we need to add counterterms, and they have to be properly quantized. There's interesting relation between this story and S-duality in the bulk. So we take the four-dimensional theory on half space, and we put a boundary, and we apply S-duality in the bulk, and we find the interplay between that and the duality that we have just discussed on the boundary. And this is the connection to Witten's S and T operations on three-dimensional field theories, so everything here matches together. And it can be generalized to arbitrary n and k. It can be generalized to arbitrary n and k. Remember this long list that I had? All of them follow from that. And that involves some interesting subtleties. First, we had to make a more precise version of level rank duality. There are a few subtleties there that have to be clarified. It turns out that it's not as trivial for large values of NF. It works only for sufficiently low values of NF. And it leads to, again, many more dualities. So on the checklist, this is what we did. Oops. That still needs to be done, and I think I'll stop here. Thank you.
Any questions?
You mentioned that you build a large class of the 3D duality from compactifying 4D dualities about one cycle. So can you, if you further compactify on one more cycle, do you get more duality back in 2D?
Okay, this is a very interesting question, and I encourage you to go to Brian Willett's talk in the parallel sessions. I forget when it is, and he'll address precisely this question. Taking a 3D duality, compactifying on a circle, and what kind of two-dimensional duality do you find? So, yeah, he will give you more than you wanted to hear about it.
I want to shoot about a piece of it became a theory. The three-dimensional real symmetry of three, it became a theory seems not to be the self. But people often discuss the particle what is directly inside itself.
Inside what?
Inside it became a theory.
Okay,
I just repeat my question. So it seems the three-dimensional real symmetry of a became theory is another theory. Yes?
Yes.
But some people discuss the particle vortex duality just inside this theory.
Yes.
Is this a puzzle or?
No, in fact, it confirms the same story. So there's three-dimensional mirror symmetry that maps two different three-dimensional theories, and the particles of one are so the statement of the mirror symmetry is a statement about a fixed point. There are two different descriptions of the same non-trivial fixed point. And very much like in this theory, we can deform it. Once we deform it, we have particles or vortices, or both. The fixed point is a fixed point. There are operators that should be mapped. As we move away from the fixed point, there is a duality between the massive spectra on the two sides, and this duality involves transformations from particles on one side to vortices on the other. In that sense, it's similar to particle-vortex dualities, and in the original papers about these dualities in 3 dimensions, this was one of the tests that was used. Now we see that it all fits nicely in a much bigger picture. So there are supersymmetric dualities which map particles and vortices, and there are non-supersymmetric dualities that map them, and it's connected all to the old particle-vortex duality from the early 80s. So we have kind of a huge structure of dualities. None of them can be rigorously proven, but they're all connected, and if you assume one of them, you can derive others.
Okay.